Swayam Prabha. Digital India. Educated India.
So welcome everyone for this day 2 of the summer school. My name is Neha Karanskar. I am a faculty in the Computer Science and Engineering Department at IIT Goa. So in today's section, we are going to do a review, a basic review, and we are going to focus on this aspect here. So essentially the links between computer architecture and operating systems. Okay. So it so happens that when we do these subjects, usually happens that we focus on the hows of the layer, like how do you design sequential circuits in digital systems, how does a processor like MIPS work, okay, how do you do scheduling, etc. in operating systems and so on. And sometimes we miss the links between these subjects, right? So the focus of this session is to understand the link between computer architecture and operating system to some extent, okay, and also look at some features that are provided by modern processors that help the operating systems in providing the functionality that they provide. Okay, and this is going to be sort of a basic review. Think of it as a recap of the concepts that you have seen. There are going to be some hands-on demos that will be useful. Okay. So when we write a high-level program, let's say this C program, the programmer's view is kind of abstract. So for example, we might think that the variables A, B, and C are in the main memory. The program also resides in the memory. Okay. The CPU somehow fetches these instructions one by one, updates the variables that are also in the memory. And the user program, the user when he's writing a program might assume that they have access to some routines like this printf, which are also in memory, which we can call, right? And via these routines, we can access the devices. So this is sort of a programmer's view. If you go one step deeper, say if you're doing some assembly level program, okay, the programmer needs to know something more, right? So here is an assembly level program where we are moving the value 2 to register R1, moving the value 3 to register R2, adding the two registers and storing the result in R3, and doing something else like some branches and so on. So when we are writing assembly level programs, a programmer needs to know about what are the registers in the machine, okay, and something about addresses, right? Where are things located in the memory? So in this processor example, typically the programmer needs to know about general purpose registers, that there are some special registers like the program counter, which keeps track of the current instruction being executed, and stack pointer and so on, right? So how does the execution happen? So I'm sure that there was a nice recap of this in your courses and also in the previous session. So basically, a program counter basically just keeps track of the current instruction being executed. It's 0 when the processor starts. And so the instruction at this location is fetched. It is executed. The results are written back into the registers. Then PC is incremented. The next instruction is fetched and so on, right? And the interface between this processing unit, the CPU, and the main memory is a data bus and the address bus. And at this level, the programmer views the main memory as simply an array of bytes. Okay, so these are byte addresses. So if the first instruction is 32 bits, that is 4 bytes. Then the first instruction, if it is at address 0, the next instruction begins at address 4 and so on, right? And we have the instructions, the code, as well as the data in the main memory. So if you have done any assembly programming, for example, if you have written simple assembly level programs for MIPS simulator in your architecture course, or if you have done embedded system programming where you are writing bare metal programs that execute directly on a processor, and there may be no operating system, or if you have written small programs for a kit like in 8085 kit or something like that, okay, then this is the view that we have, right? So from this view to this view kind of abstracts out the exact memory addresses, because we don't have to keep track of the memory addresses here, right? And also we keep track of the variables by their names. We do not have to keep track of which and how many registers are there in the CPU, which registers are free, which are being used for which variables, and so on. So this is a more detailed view, and the high level language provides a nice abstraction to the programmer. Now, if you see any real system, a real system in the sense, I mean a more complex system, it's very likely that it has an operating system running on it. And it's not just running one process, right? So there may be multiple processes running on the system simultaneously. And the operating system provides a layer between these processes and the hardware. The hardware being the processor, the CPU, time, the utilization of the CPU, the main memory, and other peripheral devices like disks and input-output devices. So essentially, the operating system provides two things. The first is that it provides hardware abstraction. It means that the user programs or the user doesn't have to know the nitty-gritty of talking with these devices, right? See, for example, if you want to write hello world to this LCD display, this display may have some registers, you may need to know their address, you may need to know a control word, status word, and so on, right? And then when you write a certain string into the control word, it will display the data that you send. So all this nitty-gritty can be hidden from the user, and the user programs can simply use a printf function, okay? And this somehow gets translated via the operating system, and it is the operating system that actually does the job for you of sending the text. So note that if you use the printf, and if you have such a LCD display, then there will be an appropriate code here in the operating system, in particular device driver, that will do the job for you. On the other hand, if you have a monitor, then there'll be a different device driver, or a serial port, a different device driver. But all the user programs still need to just know about printf, right? They don't need to know the nitty-gritty of the hardware. The same is the case for accessing any other peripheral devices, including disk. So this sort of simplifies and abstracts out the hardware to the user programs. Okay, so this is the first function of an operating system. The second function is resource management. So the operating system manages the resources, the CPU, main memory, and access to the peripheral devices, and shares them between these processors. So operating system takes care of things like fairness, whether each processor has a fair share of the resources. It also takes care of protection. So if multiple users are using the same system, one user should not be able to mess with the other user, right? The processes should be somehow isolated from each other. So this isolation, security, and a fair sharing of the resources is also provided by the operating system. So when you look at this view, the operating system itself is a program. Okay, so for the purpose of this session, we are going to be thinking of a single core, okay, just for making things simple. So we have a single core, And that looks something like this, right? There are registers, there is an execution unit, and so on. And that's able to execute one instruction at a time. Okay. So this is what we will assume. So how does the operating system, which is also a simple program running on the processor, provide these features? Okay. So how does it abstract out hardware? Well, by providing some nice interface to the user programs, right? Where user programs only need to know a particular function, and then the operating system will somehow do all the nitty-gritty. It will have the specific code required for each device. Okay, so that's fine. But exactly how does a process access the operating system? How can a user program call some routine which is part of the operating system program? Okay, can I write a program that calls operating system routines? And what is the mechanism by which I can do that? So that's what we are going to take a look at. The second is resource management. So how does the operating system provide isolation and security? So you may be aware, most of you may be aware, that an operating system provides multitasking. That is, if you have a single processor, single core, then if there are multiple processes running, let's say there are 3 processes running on the system, each process gets a share or a time slice. So process 1 executes for a certain time, then it is swapped out, process 2 is running, and so on. Okay, so each process runs for a small amount of time, and this gives an illusion that all of the processes are running at the same time. This also results in an efficient use of the processor. When, say, for example, process 1 needs to wait for some data. Let's say it invokes a get C function, which is like a get a character from the input. So it needs to wait for the user input. So while it is waiting, another process can be run. So this is multitasking, and this is what happens. So we are going to see how this can be achieved. Okay. The second is isolation and privilege levels. So if you have the operating system, which is actually managing all the resources, it makes sense for the operating system to have sort of a high privilege level. Only the operating system should be able to do certain things like directly accessing the device registers and so on, right? So the operating system should somehow have higher privileges than the other processes, the user mode processes running on the system. But how do you do it when the operating system itself is a simple program running on the same core? How do you achieve that? Okay, so many processors provide privilege levels. Okay, that means the processor can be either in the user mode or supervisor mode. So let's say the processor starts off in a supervisor mode and the operating system is running. It can do anything in the high privilege mode, like it can run all of the instructions, it can access all of the memory locations, and so on. When the operating system wants to pass control to a user mode process, the processor mode is changed from supervisor to user, and the control is passed. Here, the process has a fewer set of privileges. It can only access certain kind of instructions and so on. Okay, and then when the user process wants to do something like call a kernel routine, it uses the mechanism of traps. So this is what we will see in the session today. How does it exactly happen? Okay, how are these privilege levels implemented in a processor? So this is one way that an operating system can provide isolation to different processes. Another important mechanism is through virtual memory. So process 1 cannot directly mess with, let's say, the variables or the code of process 2, right? The other one is hardware abstraction using system calls. So the operating system provides a nice interface for the user processes to use the services provided by the kernel. Okay, so these are system calls. So what I would be doing is to make this a bit more interactive and to get feedback from you all, I would once in a while ask a few questions, and those of you who want to answer it can just write in the chat window. Okay, so here's a quick poll. How many of you have used system calls or written programs explicitly using system calls? Just want to get a quick idea. Okay. Okay, I would also like to ask how many of you have done any kind of assembly programming? I know that a survey was taken, but there are some questions I still need to ask. Okay. Have any of you done some assembly programming, either for a computer architecture course, like um, for running on a MIP simulator or something like that? Okay, about 3 of you, 4 of you. Good. And I think maybe some of you have used 8085 architecture or MIPS or some microcontroller. Can some of you write in the chat window what architecture you have studied for assembly programming? What processor architecture you have studied before or you're familiar with? Is it okay? Many of you are saying you're familiar with the 8085. Some of you are familiar with ARM. Okay, excellent, excellent. Okay, so thanks. So I hope that I think I understand that you might have written some simple assembly programs in a kit for typically the 8085 no, for educational purposes it comes with a kit or a simulator. Okay. Similarly for MIPS there is a simulator and so on. Okay. So this is essentially what I wanted to know. Thanks. And from the survey I understand that some of you are familiar with operating systems, some of you are not. So I hope that in this session, we look a little bit deeper into these layers and we understand the links between them a little more, right? And what I'm going to do is give some concrete examples. So I hope that you will be motivated to look deeper into these things. But this is an overview. We are not going to go too deep into any of these topics because it's just a one-day session. But I would like to give you enough references, links, so that you can go back and take a look on your own and dig deeper into some of these topics. So we saw the operating system view now, right? So what does the operating system provide? It provides some way of sharing the resources. One example is sharing the CPU across multiple processes. It provides some sort of isolation to the different processes running. Okay. And it provides hardware abstraction using system calls. Now the question is if the operating system is also a program running on the processor. You might imagine it's the same program, is kind of similar to the assembly programs you have written, because at the end of the day, it's converted into machine level instructions, right? So what is different about the operating system that it can achieve all these things while a user mode program cannot? Okay. So the goal of this session today is to understand some key architectural features that support program execution and the functioning of an operating system. Now, in your computer architecture course, you might have studied instruction sets, and essentially that a processor will have an instruction set, a set of instructions that it can execute, and some encoding for each of the instructions, and it has some set of registers and so on. So it's defined by an instruction set architecture, right? But other than that, There are features in a modern processor, like for example, a memory management unit or an interrupt system, a trap system, an elaborate system for interrupts and traps, which helps the operating system or other programs be interactive. Okay, they can be interrupted and so on, and that works nicely. Okay. Another thing is a processor sometimes provides different modes, like a user mode and supervisor mode. So these features actually are very essential in the operating system to do its job nicely and easily, and are sometimes not emphasized in a computer architecture course curriculum. So they are sort of dealt with later in the course typically. So that's where we will be focusing. So we will not be focusing so much on the processor architecture, instruction sets, and so on, although we'll be doing a quick recap. So essentially, we'll be looking at what are the mechanisms that a processor provides that makes it easy or sometimes even possible for an operating system to provide multitasking, isolation, and hardware abstraction. Okay. So the key components that we will be seeing in this session are first the virtual memory. So virtual memory is essentially an idea. It's not an architectural feature. Whereas a hardware unit which provides support for virtual memory and is typically present in modern processors is the memory management unit or the MMU. So we will first see the basic idea of virtual memory, and then we'll see what a typical MMU looks like. Second is privilege levels. So essentially, the processor can be either in the user mode or supervisor mode, but how does it switch between the two? How come a program running in a user mode cannot simply jump to the supervisor mode and do some things there, right? How is this separation provided exactly? How can you jump from the super? How can the kernel pass control to the user and go into the user mode? But a user mode program cannot suddenly go into supervisor mode and do some malicious thing, right? So how is that provided in a processor? And the third thing is traps. Okay, so essentially the idea of trap is something similar to the interrupt, but it's more the more precise term is trap, because with an interrupt you might imagine an external interrupt like a pin of the processor, and if there's a pulse on that pin, then the processor is interrupted, and then the execution the control moves to an interrupt handler and something is done. Right? So interrupts are necessary for providing interactivity to the program. Right? Respond immediately to some events. But there can be things caused by the instruction execution itself, not by external events. Or sometimes the user may want to simulate something like an interrupt by calling an instruction. So a trap is a generic term encompassing all these kinds of events, which are sudden events which have to be responded to immediately. Like the control flow has to jump to some code which handles these events immediately. So these are called traps. So we will see these three components in today's session. Essentially, how they are implemented in a modern processor. Okay. The second goal of this session is to understand the links between these three views. The programmer's view, let's say if you're writing a C program, how does that translate into the architectural view, where you're dealing with registers and memory addresses and so on? And how does that translate to how the operating system runs, how do multiple processes run, and so on. So the goal of this session is to understand the links between these layers in slightly more detail, although not this is going to be an overview, so we're not going to be going into too much detail, but essentially I hope that at the end of the session you will get a nice idea of the links and be able to see the integral picture. Okay, so when I'm going to explain these ideas, I might need some concrete examples, right? So for this, I have chosen the Spark V8 processor architecture. It's an instruction set architecture. So why have I chosen this architecture? Okay. So Spark V8, it's a 32-bit processor, and it's a RISC architecture. So RISC stands for reduced instruction set architecture. Basically, so what it means is that the variety of instructions that it supports are a minimal, elegant, well-designed set, okay, which makes the execution more efficient, the decoding of the instructions faster, the processor more power efficient, and so on. So basically, the processor supports a small, minimal, elegant set of instructions. And a high-level program, let's say a C program, is then converted into a sequence of these minimal machine-level instructions. The other variant is CISC, which is complex instruction set computers. So Spark V8 is an example of a RISC architecture. Okay, so quick quiz here. Please type in the chat window. What other processors are you aware of that have a RISC architecture? I just like to know if you're aware of any other RISC architectures. Okay. Also, Spark V8 it's a well-documented standard. In fact, it's an IEEE standard, the instruction set, and it's a mature. It started in the 1980s, as used in many processors. For example, by Oracle and so on. Fujitsu made many processors using this architecture. Surprisingly, so V8 is a 32-bit architecture, right? So modern processors on your laptops and all are 64-bit. But although this is a very old architecture, it's still in use for specific applications like radiation-hardened processors and space applications and so on. Now, one important reason for choosing this is that it's a simple architecture, yet it is rich enough to understand all the features in a modern processor. So essentially, these features that I wanted to talk about, these three features, there is a MMU, which is part of the reference. It supports privilege levels. It supports a rich set of traps. So it has all the nice things that are there in a modern processor, yet it's a simple architecture. And it's often used in many computer architecture courses across the world for teaching. So if you want to understand the architecture, the entire architecture can be understood in a few 100 pages document here. It's not as big as a book, actually, it's smaller. So this is a single document that nicely defines the architecture. Okay, ARM, okay, MIPS, RISC-V, okay. So Intel, so generally the architecture is called x86, okay, because it's, though Intel is the company that started this architecture, there are other companies that also use similar set of instructions like EMD and so on. So the architecture is called x86, and it is not a RISC. It's a complex instruction set architecture. And we will see a cute example today of what is that. Okay. Essentially, I'll show you assembly code generated for my laptop that I'm using, which is a Intel processor. And I'll also show you some assembly code for a Spark processor and show you how it's different. So in today's session, we are going to be using these very useful tools. If you are not familiar with any of these tools, I would highly encourage you to download and learn these tools. Because anyone who wants to do something hands-on with computer architecture, to observe, to do something, to really understand, these tools are very useful. They are open source tools. They're part of the GNU toolchain. The first is the GNU compiler, GCC. It's actually a toolchain. It's a set of programs for doing different things, like compiling a C program into assembly. Then an assembler converts the assembly level program into machine instructions, that's object code, and so on. You have the linker and so on. So it's a tool chain. Okay. You have the object dump utility. It's useful for viewing object files. So if you have an executable and you want to look at what are the machine instructions, what are the assembly level instructions it is made up of, okay, and what are the memory addresses in that object file, you can look at it using the object dump utility. And finally, you have the GNU debugger, which is like very useful in debugging programs. Like say if you're getting a seg fault, you can step through your program and reach the point exactly where you're getting a seg fault and examine the values of the variables and so on. So it's a debugger, but it's much more than that. You can use it to even step through the assembly level instructions, not just through one line by line in your C program, but you can use it for debugging assembly level programs and so on. So it's a very powerful tool. And here are some tutorial links on these tools. So I'll be using some of these tools in the morning session today. Okay, and here's a quick overview of what we will see in today's session. So we will start with a quick review of basic instruction execution. Essentially, start from a C program and see how the machine level instructions get executed on a processor, right? Just a quick review. Once we do this and we'll see some demos and we have a concrete picture in our mind of the basic instruction execution algorithm, we will move on to virtual memory, paging, MMU, privilege levels, and traps. Okay, so essentially the first is a more important idea requiring more of your time. The last two can be discussed relatively quickly and you will understand them because they are very simple ideas, privilege levels and traps. Okay. So with that said about the overview of the session,